Alright, welcome to the lesson on characteristics of sound. So what's today's goal? I can explain the various characteristics of sound and apply them to real-world phenomenon, so like beat frequency, nodes, etc., etc. So we're going to talk about a couple of things today. First thing, an oscilloscope. Oscilloscope is something that transforms sound energy to a graphical representation of a wave. Now, the problem I talked about earlier in this unit was that sound waves look like this. Series of compressions and rarefactions. So we have a compression, rarefaction, compression. And like I said, mathematically, it's not a very nice model to work with, but what we have developed over time is an oscilloscope, which will take this information, and what it'll do, it'll transfer those compressions and rarefactions to a nice sinusoidal graph for us, which allows us to do analysis and play with it a little bit when it comes to changing frequencies and stuff like that. When you do sound mixing and so on and so forth. So the oscilloscope is a nice piece of technology which allows us a little bit easier way to develop and work with sound waves and resulting mathematical models. So we're talking about frequency and sound. We want to talk about the different waves that exist out there. So, in terms of sound waves for frequency, if the frequency is higher, which means that there are more waves, compared to a frequency with less waves, that looks like that, you'll notice the amplitude stays the same here. Alright, so I'll just put this in as a side note. Amplitude stays the same. Okay. What does that mean when we're comparing these two sources of sound? Well, a higher frequency results in a higher pitch. Alright, think back to the Doppler effect. If the waves are striking you faster, the pitch is higher, whereas this would result in a lower pitch. So when we're talking to the musically minded people in here, we're talking about when you're changing your pitch, you are changing the frequency at which you are creating crests and troughs. What happens if we adjust our amplitude? What would that look like? Well, I'm going to maintain the same frequency this time. However, oops, probably dipped a little low there. However, there's your resulting change. So this time, frequency stays the same. And what happens is an increase in amplitude, okay, resulting in more energy being input, results in a higher volume. So amplitude and volume are connected, all right, and frequency and pitch are related. Okay, so that amplitude is the relation, or directly related to volume, and your frequency is directly related to your pitch. So those are what you're adjusting for people that are playing musical instruments or singing. Those are the things that you're controlling or working with. So let's talk about interference and beats. So when we have two waves with different frequencies, all right, so they're occurring at a different rate, it results in both constructive and destructive interference. It creates what we call a beat. So a beat is a full cycle of loudness, and I do believe I have an app, and you can go to that and you can try the beats rather than the graphing calculator exercise. It's neat mathematically, but it doesn't really give you an idea of what that is. So please try the applet once you're done the video here. And what results in the graphing calculator is we get this pattern here. Let's see if I can do it. So if we had two frequencies, we would end up with an oscilloscope, which show us this. And those there, that loudness, okay, this would result in a loudness. And you'll understand it when you try the applet. Loudness, the result is what we call a beat. All right, and you can try with the tuning forks. Probably have already. I think that's one of the activities that have you done that you've worked with already. The tuning forks. So the tuning forks, when one frequency is changed. So when one frequency is changed, beats can be detected. Where you have moments of loudness. Moments of loudness. All right. So beat frequency, let's talk about that for a second at the bottom here. So beat frequency is F2 minus F1, and for those that are wondering, those vertical bars are absolute value. Absolute value, which means that F2 minus F1 is always a positive number. That's all that means. So no matter what, whether it's negative 30 or positive 70, it's always going to be a positive number, so it'd be positive 30. And the formula then for beats is as shown here. Okay, so there is a formula, actually two formula, that you want included on your study sheet. N is the number of beats you detect. Number of beats. And your delta T, of course, is your time in seconds. So how many beats you heard in what amount of time. Okay, so as we move on then, we can use those formulas to deal with an example like this. So in a tuning fork with a frequency of 512 hertz and a tuning fork of unknown frequency are heard together for a period of 4 seconds, there's 20 beats. So we know that the number of beats is 20. We know that our delta T is 4 seconds. So that allows us to find our beat frequency. So from the previous slide at the bottom, using that last formula, we can calculate our F beats, frequency of the beats. And that is your N over delta T. So 20 over 4. And that's equal to a value of 5. So 5 hertz. Okay. So because the beat frequency is 5 hertz, that means that your frequency of beats is equal to, so there's, and maybe I better clarify this as well. F2 minus F1 is equal to your N over delta T, which is equal to the frequency of beats. All right. Before I cause any confusion whatsoever, all three of those are the same thing. So as I go into this now, I know that I want my beat frequency to be 5 hertz. So if I have 512 minus F1, there's actually going to be two answers, okay? Because when you solve dealing with absolute value, you have 5 could equal 512 plus F1. Maybe we'll just keep it simpler here. So what value will give you a difference of 5? So therefore, F1 would equal 512 plus 5, or 512 minus 5. That's probably the simpler way to do it. 517 hertz, or taking that away, 507 hertz. So there's two possible answers here, so you don't actually know what the other tuning fork is, but you know it's going to be either 517 or 507. So you have kind of a range to work with here. All right. Okay, so moving along then, let's talk about standing waves for a second. And again, I'm going to let you look at the applet yourself. So I've kind of freehanded the waves, and you can do the same thing, or you can visit the applet and see exactly what you need to draw here. But a standing wave occurs when a wave reflects back on itself at the same frequency and have the same wavelength and speed. So the resulting wave has a particular pattern. So what I have here, I've drawn a wave and I've tried to move it out of phase. So I have two waves, they're identical. I've just drawn them out of phase a little bit. So I'm going to use my green marker then to kind of identify the resulting wave. So basically what I've decided here, that these 2 points are going to be destructive interference. That's where I'm going to have a node of 0. Similarly, to me it looks like right there, we'll have a nodal line. I'm going to have constructive interference, or a super crest at this location. I don't want it right there. So that's where my super crest will occur, and my super troughs then accordingly, or head off accordingly. So, oh look, something like that. So here are my nodal points, and like I said, if you go and use the applet, this will look a little, much better. Okay. So anyway, those are my nodal points. I've sketched the same waves down below. I've just kind of used the computer to twist them around a little bit, and you'll notice it lines up. I'm going to have a destructive interference in the exact same location, and similarly, it's off a little bit. I wanted to have destructive interference there as well. And here is where that super crest or super trough, I've kind of skewed a little bit here. But anyway, gives you a general idea of what's happening. So at the end of the day, what I'm looking for here is that those nodal lines don't actually move. Okay? Those nodal lines maintain their same location in a standing wave. Alright? So, what I want you to take from this then, a couple of points. First one, the nodes do not move, and you'll see this in the applet. So please go ahead, you can pause right now and go do the applet, but you'll see that no matter what you do, those nodes do not move. Alright. Second point, the crest and trough, or the crest slash trough locations do not move. So this green wave that I've created here, okay, it will stay stationary. It just fluctuates up and down. So you can see up here, it started out as, I had it drawn as a trough. Now it becomes a crest, so they don't move as well. They remain in the same location. And the third point that I want to look at here, or make note of, is that standing waves create super crests and super troughs. Super crests and super troughs. Okay. So those are the 3 points I want you to take away from standing waves. If you have a standing wave that's out of phase, okay, or reflected back on itself, the nodes will not move, okay? The second thing is the crests and troughs of the new wave that's created also will remain in the same location or do not move. And finally, you get super crests and super troughs. So I do encourage you at this point, I'm going to end the video at this point and finish up in the next one, but please take a look at that applet that I've got posted there, and it shows it a lot better. And if you want to copy and paste it into a document and print it out for your note, probably a smart thing to do. We'll see you in the next video.